right, let's draw the shear, force, and bending moment diagram for these two. Again, I'll shortcut this a little bit, and we'll talk about shear and moment. So this is going to be the shear at this end is going to be positive P over 2, and the shear at this end is going to be, this is positive, right? But it's going to be actually negative P over 2. What's the moment here? 0. What's the moment here? 0. So we've got some good start and stop points. So let's begin there. So again, we'll start with the shear. We'll work from left to right. So starting at the left side, what's the value of the shear? Positive, and has a value of P over 2. And we know that the change in shear is the area under the load curve. So over the first half of the beam, L over 2, what's the area of the load curve? 0. So there's no change. So I'm going to stay at P over 2. And the curve that connects these 2 points, remember, it's given by the value of the load. So the slope of the curve is the load. And the load is 0. So we have a 0 slope, and that gives us a horizontal line. Now, as we go from the left side to the right side, what should the change in shear be? P, and it's positive or negative? So if I'm at P over 2, and I subtract P, what do I get? Negative P over 2. By the way, what should I hit on this side? Negative P over 2. So that says that the change in shear between these 2 points should be 0, and it's given by the loading, which is 0. So that works out great. And the slope? The slope is given by the value of the load, which is 0. So that means we have, that's it. So there's your shear diagram. So what's the maximum shear in the beam? P over 2. The only thing is it changes direction. That's really not a problem for most shear connections. You just design it for the shear value, not for the direction. Okay, let's do moment now. What happens at the moment diagram? Well, what's the value of the moment at the start of the beam? 0. What's the value of the moment at the end of the beam? Alright, so let's use our relationships. We know the change in moment is the area under the shear diagram. So you see this part of the shear diagram is pretty constant. So let's look at the change in moment from 0 to L over 2. It'll be this area, which is what? P over 2 times L over 2. And that's a positive area. So that means I'll change to a positive value of PL over 4. What's the shape of the curve? Well, I know the slope of the moment diagram is equal to the shear. And what's the value of the shear everywhere? It's constant, and it's positive. So here's a constant slope that's positive. In fact, if you looked at it, you would see that it is P over 2 rise for every 1 run. The change in moment from L over 2 to L is this part of the curve, which is what? It's a negative area. L over 2 times P over 2 is this. So positive minus the negative, 0. And the slope is equal to the shear, and the shear is constant, and it's negative. So if I looked at that, I would have 1 to minus P over 2. There's your moment diagram. So where's the moment maximum? Well, that's the value, and it's maximum right in the middle. Pretty cool, right? Let's do another one. So let's look at now a uniform distributed load. So again, I'm going to see the shear here is going to be positive W naught L over 2. And the shear on this side, which is positive down, is going to be minus W naught L over 2. I think you can figure that out if you looked at it closely. What's the moment here? 0. And the moment here? 0. So we have our starting and end points. We should be in good shape. So that means our shear diagram will start with a positive value of W naught L over 2. And it should end with a negative value of W naught L over 2. Let's see if we can make it work. So the change in shear between any 2 points is the area of the load curve. So what is the area of the load curve over the whole length? W naught times L. And is that positive or negative? Negative. So if I start at WL over 2 and subtract WL, I get negative. That worked out. What's the shape of the curve in between? How do you know that? Well, the slope of the shear diagram should be equal to the load, and the load is constant. And what kind of value is it? Positive or negative? Negative. So it should be a constant slope. I'm not going to be able to get this to scale. I'm trying to squeeze it in. There it goes. Now across the axis, when it crosses the axis from positive to negative or negative to positive, that indicates a point which will be of interest to us. So I'm going to add that point to my moment diagram. And why would I care about that? Well, that's where the shear is 0. So if you come down here and you say the shear is 0, what does that tell you about the slope of the moment diagram? It is also 0. What does a 0 slope tell you? You may have hit a maximum or a minimum. That's why we want to know that point, because that will tell us probably where our maximum or minimum moment might occur. So once I've established that point, how do I know what happens at L over 2? Well, what's the slope of this line? For every 1 we go, what does it drop? Minus W naught. So you can actually figure that out, right? Watch this. If I project this area back up, let's say I do it for an arbitrary value x. So what would be the area? What would be the area under the load curve there? It would be W times x, or actually W naught times x, right? And that should be equal to what? The change in shear. What is the change in shear from here to here? Is it positive or negative? Negative. So it would be negative. These two things are equal. Say that again? Oh, sorry. These two things are equal, right? The change in shear is equal to the area of the load on the curve. This is the area of the curve. This is the change in shear. Set them equal and solve for x. You'll find that x is equal to L over 2. So you should be able to find this point. So I have. It's L over 2. So now let's see what happens. So when I do my moment diagram, I know I'm going to start at 0. I'm going to end at 0. And now I can see that I have a positive portion of my shear diagram from 0 to L over 2. So my change in moment between 0 and L over 2 is this area. What is that area? Triangle. 1/2 base, L over 2, times height, W naught L over 2. That's positive. That should be W naught L squared over 8. half, a half, and a half. Okay? So what now is the slope of my moment diagram? Well, it's equal to the shear. What is the shear here? Well, it's positive. In fact, if I look at it, it is W naught L over 2. And it decreases to 0. That means I have a 0 slope here. So I can now connect those. My moment diagram should look something like that. Now the second half of the beam, from L over 2 to L, the area under my load shear diagram is what? What's this triangular area? And that's negative. You do the calculation, 1/2 base times height, you get it negative W naught L squared over 8. So that puts us back to 0. That's cool. Now, in terms of the slope, we're going to start with this value, which is 0, and we're going to get progressively larger to a maximum value of minus W naught L over 2 to 1. And when you fit that in there, oops, I didn't quite draw the curve symmetric. It should be symmetric. It should be a parabola about this line. So what's the maximum value of shear? Oh, no, sorry, I said shear. I meant moment. Sorry. What's the maximum value for the moment? W naught L squared over 8. And it occurs where? Right in the middle. Right in the middle. Any other questions before I stop this one?